All right. I'll switch to screencast now.
Actually, I didn't use any this Hangout here. So couldn't guide me actually.
You don't really have to do anything. I mean, uh, I'll be
Using the
showing
app.
my screen, and this is actually getting streamed to YouTube. So what I was planning is this will get recorded on YouTube, and people can later watch it if they feel like, getting into development. That
Sure.
is what I planned. Yeah.
Okay.
All right. So, um, give me a sec. All right. I'm going for a screencast. So now you shall be able to see my terminal, I guess.
Yeah. Very easy.
All right. So let me first show you the project structure that we have. Uh, Here it is. This is uh, the current setup that we have. So I made a few structural changes a few days ago, and that was because of the build system. I'll explain everything. So firstly, let's talk about how the app actually works. Then we can actually talk about the code. All right.
Sure.
So what we have in Electron is something called a main process. So this is, say, the main process. All right. And this main process forks many renderer processes. So the task of renderer process is basically rendering the UI.
Okay.
So in every Electron app, there will be just one main process, and depending on needs, there can be multiple renderer process. As you can guess, this is because you can have multiple windows for a single app,
Mm-hmm.
right?
Okay.
But this is the traditional setup that we have. But in case of an app that is using React for UI rendering, you usually have one window for showing all the UI. This is because React is used to create what we call single page applications.
Yeah.
So all the page changes, all the route changes and everything will happen within a single window, and we don't need other windows to show different sections of the app,
Mm-hmm.
right? So React will take care of all the rendering part, all right, in this particular renderer process that Electron will generate, and there will be just one main process. So there cannot be more than one main process in any Electron app. So you might ask, what is the task of the main process? So the main process is basically responsible for communicating with your OS. So anything that is, that may require something from the OS, an API from the OS, your main process will do that, not your
Okay.
renderer process. This is done. I don't know why this has been made this way. Maybe for security reasons. I don't know why, but this is how it works. So say you wish to display native notifications that you have on your desktop, right? So for that, your main process will do the task of communicating with the OS and letting it know that, you know what, I need the notification feature. So this is how, you know what, you should turn off your mic, I guess, or maybe lower the volume a bit.
Okay.
Yeah, all right, there we go. So then I mean this is why usually we don't uh, try to block the main process. If we block the main process, everything that has been forked from the main process will start getting blocked. So if you try to do something that is a blocking process, what a blocking process is basically a process that requires a lot of computation. So anything that is a blocking process will basically hinder the whole app. So this is why you don't do anything that requires heavy computation in the main process. Now let's say you have a renderer process. So in any traditional simple app, what you'll have is a renderer process and a simple UI, and everything is going fine. But as you know, in desktop apps, you can have um, situations where you need to do heavy computations. Like in our case, we are not doing heavy computation, but the kind of task that we are doing can be considered blocking. So we'll get to that in a minute. So, um, so the thing is, in a renderer process, now you might be thinking that if we cannot do heavy computations in main process, I mean, there should be a way to do it in the render process, right? But the thing is, the render process that will show the UI to the user, you cannot do heavy computations there as well. Now, this is because if you try to block that thread, the UI will get choked. So that is why you cannot do heavy computations in your renderer thread. You cannot do heavy computations in the main thread. So where should you do it, right? So this is where now there are many solutions of tackling this particular situation. So if you go to Medium, there is an article on this, but they don't talk about much. uh, I mean, they don't talk in details about this, so that is a problem with most of the articles that are related to Electron. They're not detailed enough. They just talk and they just talk. They don't show any code. So I think it was. I think it's this one. Uh, yeah. So this article has, I think, yeah. So this article talks about how to do heavy processing, and it will offer many, I mean, mainly three kind of solutions to deal with this situation. One is, I think, creating forks. I don't know what they are called. I don't know. I'll just share this link anyway. I don't know if it is allowed to be shared. Yeah, I've shared a link. And yeah, and one other solution is called worker process, I think. But both of these solutions have a problem that, I mean, you have to access features in these two solutions, features of Node and features of Electron as well. So the problem with these two solutions is that you won't be able to use, I mean, in one you may be able to use the Node processes while Node features, while the Electron features will be disabled and something like that. So these two solutions are not something that we were looking for. So the other solution that we have, the third solution that we have, is creating another renderer process. Now this renderer process is not responsible for drawing up the UI. The UI is being generated by this particular renderer thread. So this renderer thread is free, right? I mean, this is not responsible for UI work. So you can block this. You can have a heavy task being done in this particular thread. So your UI will be free. Your UI will be free to, your UI won't get choked, and your task will get finished in this particular thread. So this might seem familiar if you take a close look at what Electron is actually using to give you a platform to draw up the UI and everything. So an Electron is basically a Chromium shell, and Chromium is basically the open source version of Chrome. And as you know, in Chrome you have multiple tabs, and each tab is basically a renderer thread. So as you know, if one tab crashes, the other works. The other one that are there, they work. So this is how the whole thing is. So whenever you need to do anything that is blocking, anything that may require your thread to get blocked or stopped, in that case you'll drop a new thread, UI thread. But again, you'll ask, if I'm drawing up a new UI thread, then we'll have to show something, and there will be another window and everything. You just have to hide that window. So this window is basically a hidden window which has no width or height, and your task is done in this particular thread. Yes. So this is how the challenge of doing blocking tasks was handled in our case. This is what I did. Now, now there, just a sec. Now, now there was, I mean, now this was the main challenge that we had to face. So this was completely handled with a few experimentations and everything. We figured out a way to do this without any hassle. And in fact, I wrote a library to make this task a bit easier. Easier in the sense that you'll get to know why this was a challenge. But if you go to my repository and look for load balancer, this is the library I wrote for Electron, and we are currently using this in PSLab desktop. So this basically draws up renderer threads whenever you need to do background tasks. So uh, now you'll realize why I had to write this library in a minute. So now let's talk about the communication. Right, there are two processes. You know, just a second. So we have two threads running, not threads, I should call them processes. That's the official name for it. So processes. So one's the main process, one is the renderer process. Now how do we communicate between the two? I mean, they cannot, I mean, they're not sharing variables or anything, so you have to have some kind of means of communication. So this is where the Electron IPC comes in, which is inter-process communication. That's a module that they have provided. So what it does is you have listeners. You can have another listener here somewhere. All right. Now, whenever you need to talk to the renderer thread, you just fire something with uh, with the name of the IPC. I mean the listener, and this particular listener will be fired, and the function that you have written for this listener will be triggered. Same goes for the renderer thread. When you need to talk to the main uh, process, you fire up the IPC, and this will get notified, and the listener, I mean the function that you have written, will get triggered here. So if you want to see a simple example, we have it in our code. But yeah, before going to the code, let me just give you a quick tour of the structure. So in the source folder, we have everything related to the UI, just the UI. Nothing related to background tasks, Python scripts, nothing, just the UI. So this is complete React code. This is nothing extra other than that. Then we have the public folder. Now, if we are using create react app, the CRA. Now, the reason why we are using CRA is because CRA allows us to keep things updated without hassle. So one npm upgrade and we are done. So we don't plan to eject this app from CRA anytime soon, because we don't want to get into the hassle of managing webpack configs and everything. So this keeps things neat. And then we have the public folder. When you use CRA, this public folder will be auto-generated. Now the thing to note about this auto-generated public folder is anything kept in this public folder will not be touched when you use the command react build or npm build for CRA. Now, when you run npm build, everything in the source folder is modified, and it is modified in such a way so that it can be optimized. So the code is shrunk, the variable names are shortened, and all sorts of optimizations are done. But anything in the public folder, this is kept as it is. So we will uh, take advantage of this property in a while. Now, then we have the docs folder, which is nothing but the images that we are using and anything related to the documentation. Package.json will play an important role because we have written custom uh, run commands for the project. We'll get to that in a minute. Then we have the scripts folder. Now this folder hosts all the Python scripts that are there in the project. So why Python scripts? And why not use node modules? This was because the PSL library, as you know, if you go to, I mean, you know already, the PSL desktop, not desktop, PSLab Python, PSLab Python is the library they had written for communication with the board. So if you actually want to see how that might look like, you do this from PSL import science lab. Now the board is not connected, so if I try to make use of this module, it will throw error. But yeah, so this particular pip module is used to communicate with the board. Now we did not have the time to write a node module for this, so we were just going to use the pip module that we had. So this is why we wrote Python scripts instead of going for a whole JS stack. So now how this works is a completely different story, but everything was built one after the other, and a lot of changes were made eventually. So now let's take a look at the background tasks. Now here you will see HTML files. So the way this works is source, everything in source will take up one renderer thread, just one renderer thread. Now every time you open a new sec. So every time you open up a new thread, you have to give it something to run, right? So whatever the new thread has to run, the second thread that will create, second renderer thread will create this one, the one that will be hidden from the user. Now you need something to run on this, right? So for that, we have created a separate folder, the background tasks folder. So if you open this, this is nothing but JS file. I mean, it is HTML file, but it has nothing related to HTML. It has a script tag, and everything within this is JavaScript. Now, we are using just one background process for now. We might make use of another later on, but as of now, just need one. And I'll explain the contents of this later as we go through the code. So I think the project structure is clear. You can switch on your mic and let me know if everything is going fine.
Yeah, everything is fine.
Cool.
But just a
Yeah.
background. Actually, I want to ask that how you managed to write the script code. Is there any documentation for that or anything?
The
Because
Python script?
yeah,
Yeah, for that, you have to clone the PSLab Python repository.
yeah,
And there is a command. When you run that command, it will generate the documentation. It is, I think, Phoenix, as far as I remember, some Phoenix related command. And this documentation will be generated for you. You just have to open this on your browser, and like for example, if you want to know how which command to run to get the values from your four channel oscilloscope, so you can look for this command, say capture. um, Capture one will draw out samples from one particular channel, the channel name that you give, and this I think is the number of samples that you need to draw, and this is, I don't know what that is, time gap. Okay. So
okay,
this is the documentation for the PSLab Python library that we will be using inside those Python scripts.
okay.
So yeah, any other questions so far?
No,
All right.
everything's
So now let's take a look at the code. Now, like I was talking, that anything inside this public folder is not altered. Now, the reason why this property was important is because we have placed our electron.js folder, I mean file here. Now, if you take a look at package.json, it will give you important clues. Uh, any Electron app needs a main, I mean, this is the entry point. This is the file that will open up. Like uh, you have the main function in C++. Similarly, this is the file that Electron will start with. And this file usually is the main process. I mean, everything that should be in the main process is written in this file. So if you go here, yeah. So Uh, yes. So if you open this up, now everything written in this is part of the main process. So you can give it a quick read and I can explain you the code. So every time you need to use Electron, you'll have to import Electron and path and URL and everything. Here is IPC main. This is the IPC renderer. Sorry, this is the IPC module, inter-process communication module for the main process. Now you'll see its use here. But before that, let's talk about what other things that we have here. So here's a function that is imported from Electron, and main window is the object that will populate using this browser window function. Main window is basically the uh, the UI, the main UI that you have. All right. So as soon as your app starts, your app will create a UI. It will create a shell, a window within which your React app will run. Basically, now in case of here's something interesting that you should take a look. This might come in handy later on. Here we use start URL, and as you can see, here we are using an environment variable. So in this case, I have an article saved, I think. uh, Great. There was an article regarding Node.js environment variables. You can give it a Google search and you'll find it. Nothing so tricky. Uh, so variables are basically used to tell whether you are running the app in production mode or you are running it in development mode. So when you are running it in development mode, you usually pass dev equal to 1 value during your development mode. I'll show you. I think, yeah, see. So if you remember, okay, the scripts are basically the commands that you run with npm. So npm start, npm build, etc., etc. So as you know, to start the Electron app, we use npm start, and in npm start, then again, this command will run, and this command basically uses these two commands. So React start and Electron start. As you can see, we can go into details, but that would again go on a tangent, so we'll talk about this later. But as you can see, I'm passing dev equal to 1 whenever you are using Electron start, and Electron start is fired up from npm start. So dev equal to 1 will be passed whenever you use the npm start command. So when we have dev equal to 1, this particular URL will be used to populate your window. And as you know, when you use a normal React app, your npm start usually fires up uh, the browser, and this particular URL is automatically loaded. So as you can guess, what you are doing is your Webpack server is running, and this particular URL is being used to populate your Electron apps window that is visible to the user. Now, uh, if the app is not running in development mode, then this particular URL will be used. Now we can go on to that, but then again, the conversation will go on a different tangent. So let's skip that for now. So then, these details are not really necessary, but if you're getting into Electron app development, you should give it a read. Then again, if it is in development mode, you open the development tools automatically. The console tools that you see, and we open the app in maximize mode. We do that because we are not making the app responsive. So we want the we force the user to use it in maximized mode. Uh, then some nitty-gritty details. Yeah, so when the app is active, you fire up this function, create window, which was this particular function that you just wrote. And when all the windows are closed, you fire up this function app.quit, which will close the app completely. Then we have all the listeners that I was talking about in this diagram. So we set up listeners um, on the processes. So we have a listener here, we have a listener here. I mean, many listeners that will be listening to calls from different processes. So here we have, skip this line for now. I'll come back to that. So we have IPC on to render a data. Just a minute. Yeah. So to render a data, to render a config, to render a status. So these are the listeners that I have set up. One is for debugging. I mean, I use that to debug the renderer processes. So what this does is basically, these are the listeners. Whenever some IPC call is fired for this particular, I mean, let's say to render data, IPC call is being fired for to render data, then I mean, this particular function will be fired, and whatever arguments are being passed from there will be, I mean, will be sent to, and I mean, main window dot whatever there is. So the arguments will be forwarded in this case. If you want, you can just put up a console log and you can see whatever is being sent in the argument value. So this is basically a callback structure. If you can remember, this is very popular in Node.js development. So you fire up a listener. I mean, sorry, you set up a listener and you have a callback function which is triggered whenever this particular listener is triggered. So this is all there is in the main process. I mean, other than that, we have not used any advanced features from the main process. There are many things to be used, but I think that will come later on. As of now, we are doing perfectly fine without using any other features from the main process. Now, uh, now let's talk about the renderer process that we have. Are you familiar with React completely? Question.
Um, just a tiny bit, not that much actually. I've used Node.js
Uh-huh.
actually. React is a little bit
New.
new to me.
Okay.
Yeah.
By the way, any questions regarding the main process so far?
Yeah, I
Yeah.
was just to ask that let's take the example of the multimeter JS file.
Uh-huh.
In that also we have IPC main
Yes.
IPC renderer.
IPC renderer. Yeah.
Yeah. Okay, that was the renderer listener.
Yes. Yes. Yes.
Okay, okay,
So
okay,
whenever
got
you
it.
use I mean, whenever you want to use the IPC function in main thread, you have to use IPC main, and whenever you want to use it in renderer, you have to use IPC renderer. So that's
Okay.
a difference. Now, now let's take a quick look at the, you know what, let's start from app.js. So app.js is basically kind of the starting point for React. Actually, it is not app.js, it is index.js as far as I remember. Yes, this is actually the starting point of every React app which you build using CRA. But this has, I mean, this has no relevance from our, uh, I mean, for our discussion. Then we come to app.js. So you can skip all this. This is not really important. Uh, this is something important. Do you know the lifecycle methods of React?
Yeah, I'm familiar with that.
Okay,
Compo.
so yeah, component did mount and component will unmount. You know about that, right?
Yeah.
All right. So in this case, what we are doing is, I told you about the renderer process, right? So you set up different listeners in renderer process as well, so that whenever the main process needs to talk to the render process, it will fire up these particular listeners. Yes. So for that, you need to set up the listener whenever your component mounts, and you need to take them off when your component unmounts so that you don't leave memory leaks. So that is why in most of the cases you'll see, in not most of the cases, in every case you'll see I'll set up the listener in component did mount and I'll take it off in component will unmount. So in this case, we have two renderer status. So this particular listener is being placed to check whether your device is connected or not. So this listener sits there and waits for the main process. Now there is something important going on with the main process and the hidden process, but we'll talk about that later. As of now, let's focus on these two. So your main process somehow comes to know about the device status from some hidden entity, and that information is forwarded to the renderer process, and your renderer process will come to know about that by placing this particular listener. So to renderer status will listen for that particular data. So as you can see, the information that is being passed from the main process to the render process is this is connected, the message, and the device name, the port name, and so on and so forth. So this is a, a bit tricky logic that I've placed here. What it does is, um, as soon as your app mounts, it will send a request to the main process that I need to know whether the device is connected or not. This is done by this line. When that is done, uh, now this particular listener is also placed, and your app moves on. Then component will mount, will unmount, will basically tell when to remove these listeners. So basically, whenever your app closes completely, you need to strip away these listeners that you have placed. And then you have the routes that I've placed for different components. Oscilloscope will, I mean, whenever the hash router has the route value of oscilloscope, the oscilloscope component will be generated or rendered, should I say, the power source component, the multimeter component, and so on and so forth. Then all this is being rendered within an app shell. This is somewhat of uh, somewhat of a technique that I follow. I learned it somewhere, and now I'm using it as well. So what I have is an app shell. Now, if I open the app right now, I'm pretty sure my laptop will end up being really slow. So let's not do that. Uh, the thing is, you know what? Let's fire it anyway. Hold on a sec. This is basically, I mean, whatever I'm talking about right now is particularly related to UI. So in this case, um, this this particular section that you see, um, the navigation bar and the top bar, this is part of the app shell component, and whatever is being rendered within this area. Uh, this particular area is the child component of this app shell. So the routes are being rendered within this, and everything else remains static. So this is, I don't know, this doesn't really optimize anything. It's just for the sake of syntax, that's all. So yeah. So okay, then you can open up any particular component that we have written so far, and everything, almost everything is the same for every component. As of now, we are just repeating everything. So here's your multimeter component. Your multimeter component opens up, component did mount starts, and this will set up, I mean, if this component has anything to read data, a two renderer data listener will be set up, and status is being sent to these components because, um, say your device is disconnected, you don't want the user to send in a request to read data after that, right? So for that, we have set up an IPC renderer for status here as well. Now we could have passed this data from app.js as well, because we also have this particular data here, but we already placed this. I mean, we could do that actually. It will actually help us optimize, but there are a few things that we need to do here, and that is why we are not shifting this particular logic to app.js. So the thing is, whenever your app opens, uh, should I go into that detail right now? No, let's skip that for now. So then we have two more listeners. Yeah. So this is the data, and this is the status, and this is the config. So usually, I mean, in all the components, we are repeating these three, and wherever there's no data to be read, we are skipping this. That's it. So, like for example, power source component has nothing. I mean, no data. Sorry. Power source component is basically a one-way component, which means you set some config, your board gets configured. As simple as that. I mean, the board is not sending any particular data, as in case of oscilloscope or as in case of multimeter. So as you can see, we don't have the to renderer data listener here. This is your component did mount. We just have the status and config. And what exactly is the config being used for? Uh, okay, so the data is being used for, as you have guessed. So say the multimeter data is being read from the board will send that data to your main process via hidden quantity, and your IPC main will tell the render process, okay, this is the particular data for the to renderer data, and those I mean the data is being sent in the form of args, and args will be set as the state of this component, and that is how you see those numbers changing on your screen when you start reading data from the board. Then you have config status. I told you already. Config is being used for now see, when your device connects, the thing that the original desktop app, Python desktop app was lacking is, I think, whenever your device was connected, your app was the absolute truth, I would say. The term truth is basically the state. So say your power source component is set to 5 volts. You connect your board. Now you have set the power source component to 5 volts. So your board has the data that it has been set to 5 volts. Your app has the data that it has been set to 5 volts. Now, which one is the true value? Is the board true? Is the app true? In this case, both are same, so it's fine. Now let's say you disconnect the board and you reconnect it. Your board gets reset to 0 and your app is still at 5. So whom to believe? So for this, I took the decision of believing the board. So every time your board gets reconnected, it will send the configuration value from the board, and that is being set in the app. So that is why we have the status. So the status is updated whenever your board gets connected, and the get config from device function is triggered, and this function will tell the board to send its configuration value, and that configuration value is sent to the main process, and that main process will send this to the renderer process, and this is where you get the to renderer config, and all those values are being sent here and the states are set. Any questions so far? This might be confusing actually.
I have to go through actually. It's a
uh,
overwhelming idea for me.
yeah yeah, I know, actually it's kind of tricky, and uh, yeah, I can understand actually. um just a sec. I'll give a schematic diagram for this. Now you have your main process here, and say you have the device. Okay, now you have your render process. I'm using the same color, sorry man, I'm not going to change for that now. Now uh, this particular component, let's say multimeter, has some value, not multimeter, let's call this power source, that will be easier to understand. Let's say you have power source. Now the dials, the value on the dials are set to, let's say, 0. Your device is not yet connected, and you can do that. You can just uh, I'll show you actually. So you'll see that the dial values are set to some original I mean initial values, which may or may not be correct, because it doesn't matter, because your board is not yet connected, right? So you'll see that initially they are set to something. Yeah, so they are set to -5, 0, -3, and the device is not connected as of now, as you can see. Now, as soon as I connect my device, uh, okay, wait, see. So as soon as I connect my device, the to renderer status, I mean, the main process will be notified that the device has been connected. So the device gets connected, your main process comes to know about that. Your main process tells the renderer process that yes, a device has been connected. So as far as this goes, this particular chunk of code will be triggered. Okay. Now this code has this function, and this function is triggered after this. I mean, as soon as your device gets connected. So this now you can go through this function later on, but what this does is it will tell uh, it. I mean, in the diagram, your main process has a listener. Now this renderer process will tell the main process, I need the configuration values from the device. Now your main process will go ahead and fetch the values from your device. So yes, okay. And as soon as it gets back the configuration values, it has another listener. I mean, the renderer process has another listener for listening to the configuration values, as you can see here. And these values are updated as soon as this set of these set of values are sent from the main process. So now here, if you see that in practice, this is how it will go. I'm plugging in the device right now. See. So the values automatically got updated as soon as I connected my device. Now the configuration values are being sent from the board to your device. So your, I mean, to your app. So your board is acting as the source of truth. So anything that you update here will be, I mean, now the board has the value of 0.89 volts. Now if I unplug this, now my board has been reset to 0, as you know. Now if I plug it back in, the thing that should happen is PV3 should be reset to 0. And it did. So this is how it works. Any questions?
It's fine.
All right. So this is just the gist of how the app has been structured, or this is just the UI part so far. Now let's, like, is it getting too much to take? Because, what the hell? Just a sec. Sorry. Just a sec. Okay. So is it getting too much to take in for one particular meeting? Should I
No,
stop?
no. Let's continue. Actually,
All
it is
right.
being recorded. If I need to go through again, then I will.
Okay. That's fine. Cool. Okay. So now let's talk about the hidden window that we have created. Now, see, the thing is, we all we had to do was play with these listeners. Okay, you have a hidden window somewhere, and all this will do is this will also have hidden listen. I mean, this will also have listeners. This will talk to the main process, and the main process will talk to the listener depending on the situation. Now the only thing that the renderer process couldn't do is talk among themselves, so they cannot talk to each other directly. So the only way it could have been done was bouncing those messages off the main process. So this is what we have done actually. So say uh, I mean, if you go through the library I wrote, it's nothing very fancy. It's very trivial thing. I've just abstracted the code in an npm module. That's all I've done. So if you just go in my electron.js code, the file, here you have okay, the library is called load balancer. That is what I've named it. It does nothing of that sort, by the way. It's very trivial stuff. So in load balancer, initially what you do is you register all your background processes. So we have one file here. So I've registered it with the name of linker. So this linker name will be used everywhere whenever you want to talk or communicate with this hidden process. So you provide the path of the background process. So as in our case, it was linker.html, as you remember, and this name will be used everywhere in the app whenever you want to talk to this background process. So for example, in app.js, as soon as your app opens, it will ask for the device information. This device information is being fetched by this hidden process, actually, not your render process, not your main process, as I told, because that is a blocking task, so we cannot give that task to these two. So a separate hidden process is being created, and this communication is done using this particular hidden process. In fact, the information is not even being fetched by this hidden process. The Py scripts that I showed you, they are talking to the board, and this Py script is talking to the hidden process. So it's a long way, but it works, and it works pretty fast. Um, now, uh, now, if you go to the linker.html, this is how I structured my library. I think I could have modified it a bit. We may modify it later on as we need. So you have nothing special going on here. You have a load balancer on initialize. So as soon as your hidden window gets created, this particular function is triggered. Whatever is there in this particular part. If you go here in my libraries docs, you'll see I've documented this in such a way that it should be easy to work with. Yeah. So this is the code that you need to put in any hidden task. Okay. So you have everything going on here, and the blocking task code should be placed inside this. So as soon as your window initializes, anything that you need to provide while initialization will be passed like this initial values, and it will be passed on to the code within this. You'll have access to all those values. So here in linker, you have uh, we are using something called the Python shell. We have an npm module that lets you execute Python scripts. So we are using the PyShell module for that. You just have to name the script that you want to run and the version of Python that you want to run it with. Now here there is something that we did. I won't say it's something clever, but yeah, it was kind of innovative. So the bridge.py is the main entry point for your Python code. If you go to the scripts part, it is here, bridge.py. And for communication with different modules of the board, we have separate files. That is just done for structuring. Uh, Everything could have been written within a single file, but I like structured code, so I separated them. Now in bridge.py, this is a code worth looking actually. Uh, in bridge.py, you have a main function. It triggers as soon as your app starts. This is very simple code. Now we have what we call a while loop, and the while loop has a value true set. Okay, so the while loop, all it will do is it will listen for input values. Now one important detail I think I missed out is yeah. So this is your Python script running. This is your hidden renderer process now. Okay. Now there is just one possible channel of communication. That is the input-output stream. So this is our bottleneck for now. This is something I'm trying to deal with, but it works for now without any hassle. We had to cut some corners here and there, but it is working. So as you know, in your terminal, if you open any file, uh, this is generated. I mean, you're writing something to a code it's taking in input values, that's the in stream. If that code is writing something onto the terminal, it's outstream, and that's just one. I mean, that's a two-way communication. It's duplex, but we just have two channels. That's it. We cannot do multi-threading here. So that's the bottleneck we are facing as of now, but it is working. So so as you can see here, it will ask for an input. Every time this loop comes around, it will ask for a command. And here we have if statements. These are the commands that are being given uh, from the renderer process. So say you want your power source to say you want to set the configuration values of power source component. Yeah, should I say the power source component of the board? Yeah. So this is the command you will send from your power source.js, as you can see, using the load balancer send function. And this command will come all the way from the diagram that I showed, and it will land here. I mean, it will ask for the input. This while loop will enter this part and will ask for input. The command is paused, and it will search through this if list. And here you have set configuration power source, this. And when this command is matched, these particular values will be fetched from the rest of the message, and the power source component, I mean the other files that I've written, they will be triggered accordingly. They are neatly written, they are easy to understand, they have nothing tricky happening. Now, this is a blocking task. Why, you might ask? This is because while equal to true. So this particular script will never terminate until I actually tell it to terminate. And we don't want it to terminate. This is for a very basic reason. As soon as your app, I mean, as soon as a Python script gets connected with your app, you write that section for connection. This uh, the part that actually connects to the board is written in device detection. You can read that if you want. It's simple to understand, I think. So as soon as your device gets connected, your configuration uh, persists as long as your script persists. So if I terminate the script, your board gets reset. That is what we don't want. So that is why if your app once gets connected to the board, this Python script has to stay. This cannot terminate. And that is why we have while equal to true. And that is why we are using this looping structure. So this particular loop breaks only if I close the app. It breaks only if the board is disconnected. Uh, yes, those are the only two cases when this script actually terminates. Other than that, the script will run if the board is connected and your app is connected to the board. The script will keep running in the background. Any questions so far?
Very good.
All good.
Yeah.
All right. So say now other than that, all we have done is use basic threading. So say this I mean, this while loop is running in a thread, right? If you do anything blocking here, you won't be able to read commands after that. Yes, because if you block this, I mean, say you block this thread by doing something like sleep 10 here, time.sleep 10. So you won't be able to read commands after that because the whole program will stop right here and wait for 10 seconds. So you don't want that. So in those cases, we are creating a new thread whenever we need to do something flashy. So for example, we can go through the oscilloscope code. Um, you know what? Let's go through the multimeter code. That's far simpler. So as you can see, here you have the set config. So anything related to configuration is set within this object. So as soon as your app gets created, these objects are automatically created here. So for oscilloscope object is created, power source object, multimeter object, and so on. So all these values are set as soon as your object is initialized in the constructor. Now you have the set config for setting the configuration value, get config to fetch the configuration value from the object, um, start read. Now here, see, when you want to start reading, you have to loop, and when you loop, you're blocking the thread. So for that, we have to create a different thread, and that is where we are using threading. So here you have a capture loop function, which is a while loop, and we split it in a different thread and let this thread start, and the I mean, this particular object exits. So this is how whenever you start reading, even after that, you are still able to read the commands, because this now runs on a different thread, and that thread is blocked and it is none of our concern. Now, when you need to stop that thread, all you have to do is, I mean, you have to figure out a mechanism so that you can tell that thread when to stop. So for that, I have, I mean, all the functions that do this kind of task have is reading value. So is reading is set to false, and whenever you need to start a thread, you set it to true, and this while loop will keep running as long as this is reading value is set to true. Whenever you need to stop, all you do is reading equal to false, and your thread stops. As simple as that. So that is pretty neat. It works, and it's working beautifully for now. Now, uh, checking the comms. Just a sec. Oh, appreciation. Cool. All right. Huh. Um, any questions from the Python script? The loops and all, everything clear?
Yeah, that was.
Okay. Now, now let's talk about a tricky mechanism that I had to put for checking the device connectivity. Uh, for that, you have to open this file, device detection. This is again part of, I mean, this is again an object that is being imported in bridge.py, but it is an interesting file to deal with. See, whenever, damn it, whenever your script, I mean, this bridge.py is started, it will start with creating an object from the device detection class. And the device detection class has a function called async connect that I wrote. Now, if, I mean, in async connect, what this will do is it will first try to connect to the device using this function. Now, if your device is connected to your laptop, you will get an object value from, I mean, this will set to something not none, okay, some xyz value, but not none, okay. So when you initialize this object, I set this to none, and when I check for connection, I just do an equivalence check, okay. So if your device was not connected, what it will do is it will tell the, okay, back to the diagram. So say your device was not connected, okay. So it will tell the hidden process that your device status was false, is connected is false, and whatever messages it needs to send. Now you see the command here matches something, I mean, is kind of similar to the render process listener names that we used. So there was something called to renderer status. Here we have device connection status. So these commands are being read in the linker. So uh, your Python script is sending a value to the linker. The structure of the message that is being sent is some command type, some message, and some extra data, whatever there is. You can go through that here. In device detection, it is sending the type, command type, device connection status. The value is connected, and the message is device port busy or device not connected or whatever you want to send. So this is happening if self dot device dot connected is none, right? So in case it is connected, this chunk of code is run. Now this might become a bit confusing here. The logic is actually confusing. See, if your device is successfully connected, and then it will go to this else part, this particular loop, check connection loop, will start running, and it will keep on running as long as your app stays alive. And this will run on an interval of 500 milliseconds. Okay. So what this does is, if you pull out the cord on your board, this function will immediately get notified that yes, your app has disconnected, and some similar message that you saw above will be sent to the render. I mean the linker process. I named it linker because it is linking the device. So that is why I named it linker. It is just a hidden process. Okay, it's a hidden window. That's all. So now if you go back to the linker, here we have all these mappings for the types. So device connection status is mapped here, and it will send out a function. Sorry, it will trigger a function. This is not a function back actually. This is just triggering the main process, the listener that you put on the main process. So if you remember to render a status, now if you go to Electron.js, there is no such listener. I oh yes, we have actually. Sorry, yeah, to render a status. So this is basically doing the task of bouncing back the messages that I was talking about. Just a sec. So you have the linker process here, you have the main process here, and you have your UI here. You have the Python script running here. Okay, so your Python script sends some data here with some type. Your type is matched here in this types, and depending on that type, this will send that value to the main process, and then this main process will bounce that value off to the renderer process, and here your UI gets updated. Now if you now something similar is happening for your UI thread as well. I mean, if you click a button which says command start OSC. OSC is for oscilloscope. So that data is sent to the main then bounces it off to the linker. The linker then sends this data to your Python script. Any questions on this?
Uh,
All right.
yeah.
Okay, so the detection loop is kind of obvious here. So as long as your device stays connected, this check connection loop keeps running and checks if this device is connected
Yeah.
in every 0.5 seconds.
Yeah.
Now,
How whether this connection function is calling?
see, as soon as your Python script starts, see, your hidden process will get created. Now you'll ask, when is this getting created? So just a sec. Excuse me. So in app.js, whenever your app mounts, this is app.js is basically the wrapper for the whole app. So as soon as this opens, it will set up the listener and trigger this load balancer dot start background process IPC renderer linker. So this is the function I wrote, which will be used to create a hidden window. Okay. As you remember, I registered the linker.html using the linker name. So this is the name that is being used to create that particular window. Now, as soon as that window gets created, all this code will be run. And when this code is run, you'll see, there's that file. Yeah. So your instance of this script will be started. And sorry, this. And when this script starts, device detection object is created. And when the device detection object is created, after that, you run this async connect function. And this starts the loop that you're talking about, the check connection loop. And this is started in a different thread and left off. We are not bothered about that thread anymore. So it will do its job. Now, the interesting thing to note here is, if it gets connected, then all these things happen in this order. If it doesn't get connected, say it gets disconnected, and say it's not even there, the device is not even connected. So this particular message will be sent, this one to be exact. This message is sent. Now, if you remember, we also placed a listener that listens for device connection status. So to renderer status will get this value, this, and everything written in this object, sorry, output part will be received by um, this to render status. And as you can see, we are even extracting that value. Is connected message device name port. So if is connected is false, what it does is it will terminate the background script, because see, you don't have the device connected. Why do you need that background script anymore? So it will immediately terminate that background script. So if you see, if is connected is false and not of false is true, so this particular chunk of code will be run. So load balancer stop background process linker. So as soon as it finds out that the device was not connected, it will terminate that script, because you remember the bridge was running in a while loop, so it will not terminate automatically. You have to tell it to stop. So for that, the what the heck, yeah, so stop load balancer command will be executed. And what stop background process does is basically it will run this part of the code, this load balancer on finish. So this is a custom function that I wrote for the library. So what this does is basically it's a listener. So whenever you want to stop the process, you call the stop background process from your renderer thread, and in your hidden window, this function will be called. So here you see pi shell send command kill, and your pi shell, I mean the bridge will receive the command, it will get passed, and the kill command is received here, and the exit function is called. So the Python script gets killed. When your Python script gets killed successfully, you can actually open the index.js of my load balancer library. It's pretty trivial to read. Here you can see as soon as it gets killed, um, the close window. Yeah, I think I've written this somewhere. I don't remember where. Recently updated. Yeah. So when the worker is killed, your window is destroyed. As simple as that. Now, so basically in action, if I show you, give it a sec. Yeah. So as you can see, device was not connected. Okay. So all that happened. I mean, your script started, your script notified the linker process that your device is not connected. That message was bounced back from the main to the renderer process. Your listener on the app.js read that value and terminated the script. Now, I mean, that is fine. All right. Now, if you connect a device, how will it know that the device is connected? Because now you don't have the Python script to read that value, because your Python script is dead. So that is why we have a set interval basically here. So if your app was initially, I mean, your app just started, it found out that there was no device. So what it will do is on every 2.5 seconds, it will again start the process, and that whole cycle will continue. I mean, this will happen as long as your device is not connected. As soon as it gets connected, this loop is stopped. I mean, this interval is removed. Is this architecture clear?
Yeah.
All right. So every time your device gets, I mean, you can actually see this. I have the debugger in place, so you'll see. You see this number 13. So this was, I mean, this message was being sent from the Python script to app.js. You have this here. This is the debug listener that I put. So you can see that the number is 13 here. This was actually executed 13 times. Your script started, your script told the process that no, the device is not connected, your script got killed. Again, the script was called after 2.5 seconds. It checked, no device, again killed. This happened 13 times, and now I connected the device, so it stopped. So as you can see, the number was not increasing. Now, if I remove the device again, that the script gets killed, and it again starts after 2.5 seconds. Again started. See, the number keeps increasing. So that loop is running. Now, if I connect the device, that interval is removed, and there you go. Now the number 5 won't change. That means the script has started and it's running continuously, so it's not being killed, it's not being restarted. All right, so that is all for the architecture, and I think that's it, because other than that, if you have understood this, this is what we are doing for the whole communication. Everything other than that, there's nothing tricky going on. There's everything pretty simple. So here, if you want to send anything from your Python script, you just have to write the type that you are sending. So for example, this start OSC is basically the value that will be sent from the device to your linker process when you start the oscilloscope. So the data that will be read will be sent here. So you can have all kinds of pre-processing before you send this to the renderer process. So here I'm actually doing some pre-processing, and the passed output is here, and that is being sent to the main. The main will bounce it back to the renderer process. As simple as that. Same with the multimeter, same with the configuration values that the board will send. I mean, the Python script will send to the hidden process, and so on. Now, this all works fine as of now, and yes. Any doubts so far? Anything? Any question that pops in your mind? Let me know so that I can clear it out right now.
Actually,
Because
all good.
all good, cool.
All good.
All right, now let's step in the build process. So this is all development. This works pretty fine, pretty natural, nothing out of the blue. So now let's get back to the build process, and let's try to figure out what we did wrong initially and what modifications we made. So everything that you see here right now, scripts, background tasks, utils, yeah, all these were here within source. Now the problem is when you run, uh, so everything is happening in two steps because of React and Electron. Had we used simple HTML and jQuery, we would not have faced all these trouble. But as we are using React, which is being run using a Webpack server, that is why we faced all these problems. So as you can see, there are two steps for everything. Running the app, building the app, there are two steps for everything. So here, as you can see, we have React start, we have Electron start. But when you run the command, what you run is npm start. Npm start will, uh, kickstart this particular command. And as you can see, concurrently is basically a development dependency that we are using. You can read about this npm module. It's pretty interesting actually. So what this does is you tell concurrently which commands you want to run concurrently, obviously. So npm run react start will trigger this command, this one, npm react start. So when you run npm react start, it will fire up the Webpack server. Now, as you know, servers don't start immediately. It takes time to start. So for that, you have to wait. So for wait on, and that is why we have this line, wait on http colon localhost. This is the URL on which your React app usually hosts. Gets hosted. And as soon as your wait on finishes, which means your server has hosted the React app successfully, you start the npm run electron start. So this will fire up your electron electron app. You will be presented with that fancy little window, and your app gets hosted there. And how it gets hosted there, how the localhost part is getting rendered there, as I showed you in electron.js. We had that we had that part, you remember, I guess. So now same for the build process. Now, if you know, if you use CRA, it comes with something called React build. Usually you run that using npm build, but here, as we have two steps for everything, you'll have to first generate an optimized build for React. So when you run npm React build separately, you will end up creating a build folder here. Uh, I mean, in this root directory, you will end up with a folder named build. In that, now see, during development, the Webpack server hosts everything as JavaScript file, yeah, as different modules, different files, and everything. But during production, you don't want that. This is because how uh, web apps are hosted. So as you see, there are tons of different I'm sorry, JavaScript files. You don't want everything to be sent in chunks. Like your user is clicking on something, and again the network is being requested for that particular JavaScript file, and it is again sending. And this is something that you don't want to happen. So that is why when you create an optimized build, everything is packed into one bundle, and that is a compressed bundle. I mean, compression is done using different techniques, uh, but let's not get into that. So you end up with one particular bundle of JavaScript. Now, the problem that we were having is when you ran npm, I mean, when the React build was created, it took everything from the source folder and packed them into whatever it felt like JavaScript and HTML and whatever. And that was creating problems for uh, these files. So it was not even reading the Python scripts. It will completely ignore everything that is there in the scripts folder and ignore completely whatever is there in HTML folder. It will just look for the JavaScript files and everything in the resources folder. Other than that, everything is ignored. So when I first started venturing out in the build section of the app, all I was getting was a folder with build and no Python scripts, no HTML file, nothing. Now, an important thing is that everything in the public folder is copied as it is, no compression done. So that is why the main process file electron.js is placed here. And if you go into um, package.json, here you have something called homepage. So this is used this is used to tell the final build, the final app, I mean the one that is being created after the build, uh, the initial point of entry. So when you create the build using React build, your build folder will have this particular file index.js. And as you can see, according to the build folder, this is the root, and index.js is dot slash. If you open this in browser, this is equivalent to dot slash. So that is why your entry point becomes this. All right. So and everything was being copied as it is, electron.js included, but that was not enough because we needed these two sections as well. So I moved them out, uh, tried to shove them in the public folder, but that was not working either because I don't know why it wasn't working. Then I realized that we have a section. I mean, we have to write a separate section for build for Electron, and here you have to name the files that you want your final Debian packet, let's say, to contain. So the build directory gets copied, the one that is being generated after React build. The node modules are copied, and I mean, initially it was just these two. Then I realized we could have used. I mean, we could use this particular section to copy these three things as well. So here's where I got the idea of moving them out and renaming. I mean, filling this particular section. And if you, yes. So finally, that okay. After this section, React build, the Electron build runs, and in Electron build, I have used this flag for creating the Debian file for Linux. Here you have to name the entry point for the app, which is electron.js in this case. And when this particular command runs, you will be presented with with a distribution folder, dist, and in that you have the Debian file. That Debian file can be given to anyone. They can simply install it, and when you install it, just a sec, let me check. Yes, when you install it, you can access it using your simple search or whatever you have on your desktop, and you can run it like this. If you want to see where it gets installed, this is where it will get installed. I think it's OPT. Yes, PSLab desktop. See, here we have all the contents that we needed. Okay, the node modules are there, background tasks, build, everything. This is the folder I was talking about actually. The React build folder that gets created. It looks something like this. And the utils and everything is here. There's one more thing that we missed during this experimentation. There's something called an ASR package. ASR packages are used to prevent the users from opening your code. It is basically some kind of archive that Electron uses. So during distribution actually. So here, instead of these two folders, you would be having a package, an archive with app.asr written on it. And the problem is you can access node modules in JavaScript from that ASR package directly, but not the Python script. So in that case, during that experimentation, I found out that the linker process was starting, but it was not able to start the Python script. So then finally, I came to the conclusion that we should not use ASR package, and we turned it to false. And now we have everything in the open, and anyways, we are doing this open source. We don't care whether the user reads it or not. So now we have everything in open, so we are able to access the Python script and everything. And it is pretty interesting that after you have packaged that build, the app runs pretty fast. If you open it, it will open up immediately, as you can see. This is the final build actually, the one installed by the Debian package. Now there's a problem. There's a catch in this, which I have not fixed as of now. And I'll plan to do that later on. That will require me to make changes to my library actually. The problem is uh, when you quit the app, you quit the main window, not the hidden window. And your hidden window has no way of knowing whether or not it should terminate, because everything, including your app.js, gets killed. So it has no way of knowing when to terminate. App.js is not there to tell it to stop, right? So in some cases, what happens is your hidden window gets created. I'm talking about this in context of the production, not the development. The development works fine as of now. Production, I've seen this problem in production only, where your hidden process gets created and you terminate the app. The hidden process, the hidden window stays there, and you won't even know because you cannot see that window. But after a while, it will throw an error that your main process has got. It pops up some error. I know. So we have to fix that, and for that, we'll do some engineering. That should not be something that we should be worried about. Something trivial, but we'll get to that later on. Anything else that you feel like asking?
Yeah, I've actually seen in the build section also, in the development also.
What?
Actually, I'm using this issue. Actually, I'm using Windows as of
Hmm.
right now. So
Okay, okay.
whenever go to the task manager, there is multiple Electron process running in the task manager, and I have to
Okay.
kill all of them.
Do they have some kind of name assigned to
It's
them?
Electro. I will just PSLab, and if I'm currently open the Electron in the development mode, and in the task manager there were also 6 tasks running, I think, or sub process running.
Some of them may be normal, as far as I can tell, but I mean, see, technically, the way we have written the code, it should work uh, by creating two windows, one for UI rendering and the other should be for the background process. Anything extra is abnormal, but let me know if something like that happens, because we have to make sure something like that doesn't happen, because it will chew up RAM and we cannot have an app that makes the computer slow for no good reason. So we'll have to take a look at that. We have so many people in the chat and they have left after a while. That's weird. Yeah, anyway, so any more questions regarding the architecture, the code, or anything you feel like asking?
As of right now, all good. But just I have to go through all of the
Mhm.
things you have told me, and after
Yeah,
that,
yeah, exactly. Because it is kind of a lot, because I had to figure this, I mean, everything out, and this took me some while. I mean, I think I had to spend almost 2 to 3 weeks figuring everything out. We started with simple documentation of Electron, and that wasn't even enough for getting started, because I mean, those documentations are written based on the assumption that people will be using simple HTML, CSS, but that is not the case. People want to use React, and the documentation stops there. Now I had to turn to blog posts, and those blog posts are not written thoroughly. I mean, most of them are like, copy this file, do this file, do this, do that, and your app will start running. Now your app starts running, you don't know how to build it. So they don't cover those things and they leave it there. So I don't know why they do that, why people have never covered these topics, but I think we have figured out a good pipeline for creating an app, Electron app, which can actually make use of features that are not JS, in fact. I mean, we could have C++ code running alongside your JavaScript code, as long as there is a way to communicate with the C++ file. In this case, we are using the PyShell module, which lets us run scripts from Node.js. So that is kind of an advantage, and that is why we are able to use the Python scripts directly. So that works. And in fact, we had to change the architecture twice. Initially, we had scripts, Python scripts, which ran on demand. So if I had to read oscilloscope data, I'll send the command, and it will start the script, read the data, and get terminated automatically. So in that case, I did not have to worry about my hidden process my hidden process staying even after my app closes. But the problem in that was persistence again. As soon as the script terminates, every setting that you have done in the script will be terminated. So say you have set the power source value to 5, you read the oscilloscope data, and the script gets terminated, and that's it. Your power source values are dead. I mean, in fact, in that case, we hadn't even written the configuration part of power source. So it came later to me that we have to get this persistence going on. So that is why I had to put that while loop. I mean, the one that keeps the script alive, and the command-based architecture that we are following as of now. So the main bottleneck is that we just have one channel to read and write. There's another bottleneck, but that is not too much of a problem. See, the oscilloscope that we have has a microsecond resolution, and the lowest it can go is, I think, 8. I don't know. Uh, I think it is 8 microseconds. It can go lower, I think, but I don't know. Now, see, if you want to show graph to a user, now, I mean, graph in the sense real time graph. So if you have you run the oscilloscope so far? Do you have a board with you?
actually no.
No. Okay.
But I'm planning to purchase that because I'm so involved in this project right now. Um,
Okay. Let me show you.
just yeah, sure. Also, give me the link to buy this.
Link. You can
Where
ask Mario about that. He'll tell you. Um, or if you have some, damn it, if you have someone who has worked on this project, they might have the board with them, so you can borrow one if you want. Where
Actually,
are you
I
right now?
don't know.
Jaipur, Rajasthan, yes?
Jep, Jaipur, Rajasthan.
Yeah, okay. Channel 1 and sign 1. Okay. So, if you look at the code of oscilloscope.py and bridge.py, for testing purpose, we have hard coded this sine wave generator. This. So, on sine 1 pin of the board, I don't know if you can see it, but on the schematic of the board, you'll have S1 pin and an S2 pin. These are wave generators. So you can tell them the frequency of the wave that you want to generate. So in this case, for testing purposes, we are generating a 1000 hertz wave and a 500 hertz wave on S1 and S2 respectively. Now let's see. Just a sec. Oh, I forgot to screen share, damn it. You can see the app.
Yeah,
All right. Now see the pin, channel 1 pin and S1 pin is connected now. So your device is connected as well, as you can see. And when you, okay, channel 1 is set. All right. Which branch are you from again?
computer science.
Computer science. Okay. So you don't know how an oscilloscope works, do you?
Absolutely.
Okay.
But I will ask my electronic guys to.
Okay. So what this basically does is it plots the voltage versus time graph in real time. In real time, what I mean by real time is it will update the values in such a way that, not update the values. I mean, if I take the pin out in the middle of a reading, it will go to zero. That is what I mean by real time. So if you can see, if you start this, reduce the time base a bit to get a good graph. Yeah. So the sine wave is being generated and it is being read by the oscilloscope. Okay. It is pretty responsive. Yes. Now, if you want to actually study the wave, you just start the trigger value. And what trigger does is it will render the wave only when the wave hits a particular value of voltage. I think I think you can understand why this wave has not suddenly stabilized. Because this gets rendered only when the voltage value hits a particular value, and only then this wave is being generated. That is why the wave gets stabilized. Anyway, so the thing is, there are a bit of engineering stuff we had to do to get this kind of response rate that we have as of now. I mean, it's as you can see, the graph refreshes pretty fast. Now, the thing is, as you know, uh, for um, so as you know, for any I mean, for your TV or for your any video that you see, you usually have a frame rate of 25 FPS, I think. Yes. So 25 FPS gives you, no, do the math. So you'll have a refresh rate of, I think, don't remember, I calculated the value, whatever. So that refresh rate should be, I think, 33 milliseconds was for 60 FPS, I think. Anyway, so so in this case, the problem is we cannot go that low. The reason being, firstly, we have a longer communication channel. We have a Python script communicating to a hidden process, and that communicating to the main process, and the main process communicating to the UI and so on. So that takes a very long route, and that is not exactly the bottleneck. The problem is every time your I mean, there's a function that we run to fetch the data from the board, the oscilloscope data. So in that case, every time you run that code, you have to specify the number of samples that you want to draw. So let's say you draw 1,000 samples for one single channel. If you do that, you have to deal with 1,000 points, 1,000 data points. Now we have to do a bit of pre-processing. We have to make sure they are in formatted in the order the graph actually wants them to be. So that takes time, and that is why for now I think the refresh rate that we are going for is 0.075, which means 75 microseconds, which is, to be honest, a bit laggy, because 75 microseconds will give you uh, somewhere around 10 fps or something, a bit lower I think. So that is not a problem, to be honest, because usually when people use an oscilloscope, they use it with trigger, and they actually don't want to see a unstable unstable graph. And if your graph is already stable, then you don't have to worry anyway. So we have to work on a few issues, like the actual engineering that we need to do here is, firstly we need to see how we can optimize this. Can we go, I mean, we can go lower than this. Actually, I've tried this. We can go up till 40 microseconds, but the problem begins I mean, the problem starts there, because when you have 40 microsecond refresh rate, if you try to send a command from the renderer process to the script, the response rate drops in the sense, if you say stop reading OSC data, your actual graph will stop reading the data after like 1 or 2 seconds. This is because of that bottleneck I was talking about. We just have one standard input and one standard output channel, so your app is not that responsive when it is flooded with all those data. So that is why 75 is kind of an optimal sweet spot that we have. So it should not be a problem. If we can drop a bit lower, I think, I mean, we can work on this, but as of now, I think it's fine. It's not that problematic, to be honest. Uh, then we have another issue that we need to tackle is the uh, hidden window issue that I was talking about, that I'll deal with. My library needs some tweaking, so I'll get to that when we have something to show for. We have already started early, to be honest. I mean, for my GSOC, I have 3 months: June, July, and August. August 28 is the last submission date, and we are already utilizing the community bonding period for writing the code of the app. So we are already like 15 days ahead of time, and we have a few, I mean, 10 more days in our hands for this month. So we'll utilize that. Uh, yes. So one thing that I'm currently dealing with is the time-based thing, for which I needed input from people who are actually from electronics, because I don't know how an oscilloscope works. So that is why I wanted to meet Padmal on the last meeting, but unfortunately we could not. And for now, we have two things to work upon. We will improve the UI as in the graph. That I'll take care of. I'll work on that. We have the multimeter to finish, so the dial is not working. Sorry, the dial is working. The Sorry, what was the problem with the multimeter issue? Oh yeah, the 0360. Yes. Mhm. So the 0360 issue you can fix, but as far as I can tell, it cannot be fixed. This is because the way the dial is created, it is not a
Yeah,
dial which is
I'll
yeah.
look to that problem. Actually, I also that whenever I use a dial now,
Hmm.
that gave me a little bit problem to update the values. Uh, I couldn't go to the last value or matlab, I have to use a plus minus signs to go to the last value or the initial value.
Oh, you're talking about the power source component.
Oh, sorry. Yeah, sorry.
Yeah,
That's
for that actually, to be very honest, actually we need to have that uh, feature where the user clicks on the value, a model pops up and he enters the value so that he can actually give precise values if needed. The dial is just there for doing course changes, like going from 5 to 4, 4 to 10, some something like that. For finer adjustments, you can either use plus minus or you can directly punch in the values. For directly punching in the values, we haven't implemented that. For that, you have to wait a bit because I want to introduce the material UI model. So that will be some kind of universal model that will be a reusable component. So I'll have to write that, and then we'll be able to use it in all the other components that we deem fit. I'm talking about the multimeter dial, and the reason I think it cannot be fixed is because we are using an input dial, right? So it takes in values from 0 to 360, and based on that it returns a value to you. Now we have modified that component to work as a selection dial, which it is not actually. So there are two things that can be done, but no, there's actually one thing that can be done, and whatever you do, it will result in the same thing actually. One possibility is uh, you somehow map 0 and 360 together, but the thing is, as soon as the value changes from 360 to 0, it will circle back and that weird UI thing will appear. So I don't know how to avoid that actually. I have no idea. So
I will try to
yeah,
do
you
that
can go
problem.
ahead with that. You can totally work with that. There's another thing that I'll work with that is completing the multimeter component. So uh, for that, I'll have to write the code for the Python script. I mean, I have to complete that. I haven't finished it actually. I'll probably work on that tomorrow. Today, I'll probably work on the graph of oscilloscope. There are a few settings that need to be done. I'll take care of that. Meanwhile, you can see if you can fix the 0360 issue, or if you see that it cannot be fixed, there's another issue that is there. Now, the issue is emerging because of the dial, to be honest. I mean, the way we have placed the components and the way we are keeping track of the values and the angles. So, when the uh, when your app has started, your device is not connected yet. It checks whether your device is connected or not, and based on that, it gets the value. So initially, there is no configuration to start with. So the initial configuration is used, the state values, whatever is there in the constructor. Now, as soon as your device gets connected, the configuration value is sent. Now the problem is the device is not bothered about the dial values. The dial should be synchronized with the button values. What I mean to say is there should be a function which can be called with just the subcategory values. Have you seen the current code where I've renamed them? We renamed the components. I mean the options to subcategories.
Yeah.
R1, R2. Yes, I mean CH1, CH2, and so on. So for that, we need a function which can be called with just the subcategory values and everything else, including the units. You know what? Units can be, yeah, units, including units, uh, the main category, the dial value, the angle. Everything else is being figured out by that function on its own. You don't have to pass anything else. For now, I think the function takes in uh, multimeter. Yes. Yeah, the function that is being used to change the dial values is on click button, and it takes option name, it takes unit, it takes dial value. Now this I have passed to the dial itself, and whenever the dial is changed, this function is called, and yeah, this function is called, and the values are set accordingly. But the problem appears when the board sends configurations to this component. The board doesn't know anything about the dial values, right? It just knows the active subcategory. So this function needs to figure them out on its own. So for now, what happens is the dial sends values, the button changes colors, but the dial remains on that old whatever the angle was. So this is a problem. We need to fix that. So if you can figure out some creative way of not messing up the component, but at the same time keeping track of, I mean, I would suggest, I mean, there's this file, I think option settings or something like that, which has this huge array of the buttons that are being given to the dials. We can have a separate array where the mapping between your active subcategory, its category, the value of the dial, and so on, can be put. This value can be used by that function for updating the dial at the same time. I mean, it just needs to know the angle, sorry, the active category, and everything else can be updated by it on its own. So that, if you could look into it, let me know.
Sure.
Before making changes, let me know about it, so that we can figure out if we can have something better than that. Other than that,
Have you raised the issue uh, at GitHub? I will look to
sorry.
the. Have you raised the issue?
Yes, of course.
Okay.
Actually, you won't be able to see that issue because you don't have the board. So unless you connect the board, you won't be able to see that issue. But yes, you can raise that issue, and if you want, I can actually raise the issue and assign it to you if you want. But yes, go ahead. Uh, you can raise the issue in this name, uh, creating a function to update dial value using just subcategories as something like that. So you can try that, and yes, that should be fine. So any question regarding the functioning of the app or anything, like, if, I mean, while reading, after reading, if anything pops up, let me know. We can have another discussion and get more people involved. I don't know why people are so lazy. I'm giving them everything and they still don't want to work. And
That's
then they complain on the main channel that they don't have work to do and whatever, and post all those rubbish on the main channel. I don't know why people are like this. And we are doing our best, giving them our time, teaching them how things work. Man, I'm in my GSOC period. I don't even have to bother about why people are contributing to my project or not. I mean, it's not my project. What I mean to say is, uh, people should be enthusiastic about learning new stuff, right? We are actually creating a desktop app using Electron, which is kind of trendy, to be honest. And
yeah.
people just want to work with, you have seen those messages, right? I know HTML, CSS, JavaScript. I worked with Django. Is there a project related to that? Man, come on, step out of your comfort zone, learn new stuff. So that's it for now. If you need anything else, let me know.
Sure. Thank you for
All
this
right then.
conversation.
All right. Goodbye.